Let's prove Fermat's last theorem. A lot of people are fascinated with this Fermat's last theorem, which is related to the properties of space and the properties of numbers, natural numbers, integers per se. So I want us to focus on this proof. He said a lot of mathematicians have tried it, but it doesn't work. So except recently when Wise tried it. So this is the equation: x raised to power n plus y raised to power n equals to z raised to power n. Does it have a solution in integers? In z, that's can x, y, and z be an integer? So this is the start of the proof. Let us take the natural logarithm of the two sides of the equation of each term in the equation. So we take the natural logarithm of x raised to power n. Follow me as I try to manipulate this equation to see how x and y and z relate. So I'm trying to take the natural logarithm of each term of the equation. So I have ln x raised to power n plus ln y raised to power n, then is equals to ln z raised to power n. So if you apply the law of logarithm, we pick the power and send it to the back of the lane, the lane function. So we have n lane x plus n lane y is equals to n lane z. You are all familiar with the law of logarithm that I used there. So if you divide through by n, so that we have because n is common to both sides, to each term. So I want to remove that n. Don't forget, n is the general power of the equation. So I have left lane x plus lane y is equals to lane z. Okay, so if I apply the law of logarithm again, what I will have here is lane x plus x times y, sorry, x times y, because I'm combining the sum of logarithm, is equals to lane z. Of course, that is the normal law of logarithms. If you are familiar with logarithm, well, this is a simple application of law of logarithms. So I want to divide both sides of the equation by lane z, so that in the left I have all the variable, and then in the right I have just one. Okay, so we will have um, lane x, y, and lane z in one side, like this in this case, lane xy over lane z is equals to 1. Okay, so I'm going to apply another law of logarithms, which is related to dividing two logarithmic function. In that case, I have lane x y minus z. That's what the law says. We are trying to uh, resolve that equation. That's arithmetic. So lane xy minus z is equals to 1. Therefore, xy minus z equals to 1, because if you cancel the lane there, you have lane E, because 1 is equal to lane EE. Lane E, 1 is equal to lane E. So cancel the lane, you have xy minus z equals to 1. Then xy minus z equals to E. Okay. So if you don't understand why this is this, you can drop your comment under this post. So according to number theory, there is no way you can get three different natural number or three integers such that you multiply 2 and remove 1. Mind you, z is greater than x and y. Z is greater than x and y. So there is no way you can find a natural integer which, if you multiply two of them, you remove one, it will give you e. Don't forget, e is 2.7 something. It's a natural number. So that is the properties of integers. So which means x, y minus z is equal to e has no solution. It has no integer solution. There is no integer you can find that will satisfy x, y minus z, which will give you e. No integer will you multiply by itself and remove another integer from that will give you a real number, that will give you e. Is not possible. So we have proven that the x raised to power n plus y raised to power n is equals to z is not equal to zn, because it's not possible. So that's the proof. So if you find anything that is wrong in this equation, drop it in the comment.